Thank you, thank you. Thank you, London. So, how's it going, guys? Thank you for joining to this presentation, where basically we're gonna see ways to get code execution in the NFC reader that is used in point of sales and ATMs. And then we will discuss also from the attacker's perspective what we can do with these issues. Short intro about myself. I'm a principal security consultant here in IOActive, and I work in Madrid, in Spain. So I'm a guy that most of my time I'm doing reverse engineering, bare metal firmware, operating system applications, whatever that can be reverse engineered. Also, I work with hardware hacking, trying to extract information from memory, intra-board attacks, even fault injection, and this kind of stuff. Code review a lot as well, firmware, operating systems, applications, whatever. So basically, I like to break stuff and also learn new things. But also what I think it's interesting for this kind of job is to find solutions or fixes for, or mitigations for those findings, because sometimes that's also quite challenging, right? So first of all, something that is important to clarify here is that all the issues that we will see here affects like a lot of different devices and that are used in several scenarios. So we have like this kind of portable payment device that you have in restaurants, for instance. That is, we'll see that many devices like this are affected, but also this kind of devices that are used to pay for the train or the bus, ATMs, parking machines, vending machines. So a lot of different scenarios and devices that we have here. So for this presentation and for the research, we're going to use as an example this guy here. I'm going to try with one hand. This guy is the ID Tech Kiosk 3 device. I started the research with this one because I have many years of experience working with ATMs. And I knew that this guy is in every ATM, almost every ATM. Like most of the most important ATM vendors in the world are using this guy for the NFC interface. That's why I started with this, because back then when I was working with ATMs, I was wondering like, hey, it would be interesting to see if I can compromise an ATM through this guy. So we have here this is where we have the NFC chip and the antenna, and this is what is exposed to the user normally. And then through a serial cable, it's connected the board where we have the main microcontroller here. Let's see if I can with one hand. This guy here. So this is what we really want to compromise, because here's the firmware where it's receiving the credit card information in a transaction, for instance. But also, this firmware is responsible for the USB communications, because there is as you can see over there, there's a USB cable that is connected normally to a host computer. In the ATM, for instance, would be the ATM computer. In a point of sale, could be a laptop or a Windows computer, or whatever. So the way they normally work is that the ATM, the computer sends a command over USB to this guy, like let's start a transaction for a price. Then the firmware of the microcontroller is gonna process that and then communicate with the NFC chip and start the NFC communications. And then it's gonna receive the response from the card and then process that in the firmware again in the firmware of the microcontroller, and then send over USB the response with that information to the host. So that's more or less a simplified way to see how these devices work. So during a transaction, what we have is in the NFC interface, normally the reader is the one that starts the communications and sends some bytes, as you can see, to the card. The card processes that and then sends a response back and forth, these communications during a transaction. But for us, what is interesting and we want to focus is what the card is sending to the reader, because we are going to emulate a card. and then something specific to the reader, so we can achieve code execution through, for instance, a stack buffer overflow in the firmware of the reader. So in these NFC communications, of course, we have the NFC low-level stuff, but we don't need to focus that because we're gonna focus in the application layer, and we have what is called the APDUs, Application Protocol Data Unit. These are based on TLVs, tag length value, so it's very easy to dissect and understand the what's inside the packet. For instance, we have this particular APDU during a EMV transaction, where you can see there are tools out there where you can dissect the protocol, and you can see that, for instance, the SF is the file control information, which is a tag. The 6A byte is the size of the entire packet, and so on. So you can understand what is what. But basically, as you will see, we don't need to be an expert in EMV, in the EMV protocol, because for the Stack Overflow issues that we will see, it's not necessary to be an EMV expert. But yeah, but if we sniff, for instance, with the Proxmar device, the NFC communications during a transaction, what we'll see is basically the, like I said before, the low-level NFC stuff, and then at the application layer, we'll see those APDUs between the reader and the credit card in this case. Okay, so what we need first is to be able to emulate a card. There are several ways to do this. My approach was two different ways, as you will see. First, I use this the ACR 122U device, which contains the NXP PN532 chip, which allows emulation. So basically, with this reader, you can just connect through USB cable to your laptop, and then with a Python framework, you can send commands to the reader like, hey, let's emulate a card. You can start the emulation. And then with Python as well, you can interact through this emulated card with the NFC reader in this case, and send whatever you want to send and receive whatever you want to receive from the reader. In this case, I was using the RFID IoT framework, which is really useful for this. But also you can use, like I did here, is use your own Android application using the Android host car emulation. So you can emulate a car as well and interact through the application layer, in this case, with the reader. So, like I said before, all this research started because of this guy that is using ATMs, and the vendor of this device is IDTech. IDTech is a global leader in payment devices. This device that is used in ATMs is not only present in ATMs, it's also for point of sales and other scenarios. But IDTech they make Max Stripe devices, PIN pads, a lot of different hardware for payment stuff, but also software for the payment world. This particular one, I bought it from this website called happyatms.com, where you can buy parts from production ATMs. But also I bought the same device, a brand new device from IDTech, because when I found the issues, I wanted to confirm that if the issues were also present in the latest version of the firmware. But this particular one was in an actual ATM some years ago, I guess. So yeah, I bought it there. So yeah, like I said, as you can see, the antenna is, for instance, in the ATMs is what is exposed to the user, just this one, but it's what you really need to interact with. But like I said, the IDTech devices are used also in parking machines, vending machines, in retail and hospitality. This particular device also, that's another one from IDTech, which is also vulnerable, as we will see. But yeah, a lot of different places. So let's jump to the issues. So the very first thing that I did is try to see if I can extract the firmware from the microcontroller that we were talking about. First is try to see if JTAG is open. Surprisingly, it was enabled, JTAG. In this device, remember that this was from a production ATM, but the brand new device that I bought from IDTech, JTAG was also enabled. So yeah, that's great because you can extract the firmware and you can gain debugging capabilities with GDB in this case. which is very helpful for the research process and for the exploit development process. So that's good for the researcher or the attacker perspective. So yeah, then I extracted the firmware and then started to reverse engineer the firmware. In this case, a bare metal firmware where we don't have any kind of operating system, we don't have symbols, we barely have strings, and it has more or less 1,600 functions. So it's one of the toughest scenarios that you can find when you're dealing with firmware reverse engineering. So the plan here was like, okay, so between those 1,600 functions, I want to locate in the code where the firmware starts to receive data from the card, where it's parsing the information that is user control, in this case from the card. So there are several ways, but the way I found it like pretty quickly was that I was familiar with some EMV protocol stuff, and I knew that there was something called the proximity payment system environment, where basically, like I said before, the reader is the one that starts the transaction. So the reader is the one that starts sending bytes to the card over the NFC, over the air. And it sends some bytes, and some of those bytes are this particular string. So I just needed to find those bytes in the firmware, and then I located in the firmware, as you can see here. And then from here, I can start reverse engineering what the code is doing. And then I located, as you can see here, more or less, because remember, there are no symbols, but as soon as I identify some functionalities, I started to rename the function names. And this particular one, which is called receive card, is the one that starts receiving data from the card over the NFC interface. So from here, then now I can start, going deeper and deeper and see what the code is doing with the data that is coming from the credit card in this case. So yeah, so it took hours and hours to get familiar with the code, what the code was doing. As you can see here, they were having some sanity checks as well, checking the byte that identifies the size of the packet and so on. So at this point, I realized that those APDUs are up to 255 bytes. That's the maximum size that you can send. So I found some stack buffer overflows here, but the problem was that since the APDUs are only up to 255 bytes, what I found is that in those functions where I found the stack buffer overflow, I was able to overflow the buffer. But in the stack layout, I had another buffer, another local variables, so I wasn't able to reach the saved return address in the stack. Of course, you can also achieve code execution if you overwrite some local variables in the stack or other buffers in the stack. But I was a bit concerned here because I wanted to see like a pure classical stack buffer overflow where you can overflow the return address. So doing some more reverse engineering, I realized that the code at one of the very first stages of the parsing of the APDU, the code was checking if the second byte of the APDU was the 82 hex value. Then the code is going to get the next 2 bytes as the size of the packet. So in this case, if it's getting 2 bytes as the size, then we can have up to 65,000 more or less bytes. So I was confused, like, because as I mentioned before, APDUs are up to 255 bytes. So why this code is getting 2 bytes at size? Because in that way it could be much bigger, the APDU. Then doing some research about this, then I realized that there is something called extended APDUs, where you can indeed send much bigger APDUs, where, like I said before, the first byte is the 82, and then the next 2 bytes are indicates the size of the APDU. Okay, so yeah, then looking at the code, we can see that if this is the function, like I said before, that starts receiving from the card. So this particular stack buffer here in yellow, if we can receive with our emulated card more than 138 hex bytes, which is more or less 312 bytes, if I remember correctly, then we can overflow this stack buffer, but also we can overflow the other stack variables and overwrite the return address in the stack. So I saw this statically in the firmware, so I was pretty sure that this should be possible, but as usual, you need to provide proof, right? So I need to create a proof of concept and prove that. The problem is that the device I was using for emulate car to emulate the car didn't have a hardware and software support for extended APDUs. So I was only able to send APDUs of 255 bytes. So this took me some time to find a device that I could use to emulate a car and send those extended APDUs. But luckily, I found some Google forum where some people from Germany were complaining to Google because apparently there is some German national ID card that uses those extended APDUs, and Google provided an Android version that supports that, but also some Google Pixel phones have hardware support for extended APDUs. So I was lucky and I found the solution. So using a Google Pixel phone with this particular Android version that supports that, I was able to send an extended APDU. This is part of the Android application that I created for the proof of concept. And this is the extended APDU where, as you can see, at the very first bytes of the APDU is following the protocol grammar. Like here you can see the 82 value for the extended APDU, and the other 2 bytes are the size. But then, as you can see, the rest of the bytes are the typical 41, 41, 41 hex, the typical ASCII A's for the proof of concept. And then connected over JTAG, indeed, you can see here that with the proof of concept, like I saw statically in the firmware, you can get code execution because, as you can see, the PC register is with our value 41, 41, 41. So we can modify the execution flow of the processor in this case. The good thing from the attacker's perspective here is that first we have 65,000 bytes in our buffer. So I mean we can send like a lot of bytes, and those bytes can be our shellcode or our malware that will be injected in the memory in this case. So we have plenty of bytes, but also this particular device doesn't have exploit mitigation. So to weaponize this is very easy because it's a bare metal firmware. There is no exploit mitigations, but also there is no secure boot, so you can make it persistent. So it's very, very good news for the attacker. And yeah, and besides this particular stack buffer overflow that we saw, there are 21 more in other stages of the transaction, but this particular one was the one that we saw is at the very first stage of the transaction. But yeah, but there are many more, or there were, because this is already fixed in the firmware. And like I said before, I bought from IDTech the same device, the brand new IDTech Kiosk 3 device, but also the Kiosk 4, which is the newest version of the device, some other devices like the VP8300, which is used in retail and stuff, and all of them, they had the same issue because basically they are using the same code at least at that layer of processing the APDUs. They are using basically the same code, so the same bug is everywhere in all of their IDTech devices. So I'm going to show you just a quick video so you can see and understand better how this works. So here we have the Kiosk 3 device. I'm connected over JTAG, and the USB cable, as you can see here, is connected to the laptop, which is acting as the host machine. So here at the left, we have in this case, is a demo application from IDTech that uses what is called the IDTech Universal SDK. We will see more details about this later. And it's the application that you can use to interact over USB with the device, like to start a transaction, for instance. And in the right side, we have the debugger that is connected through JTAG to the device. So as you can see, I'm going to start a transaction with the application, with the IDTech SDK. And I'm gonna use right now just a normal credit card to see that it's working properly. Let me go back. There, you have the card there. You hear the beep, and then you have the result coming over the USB to the SDK application. Now I'm gonna use my proof of concept, and as you will see, as soon as I go there, you don't hear any beep. As soon as I tap the device, and you don't hear any beep because it's crashing right before the code for the beep. Okay. And in the debugger, we can see that indeed the LR register is with our data for the 41s that I was talking about, but also if we execute backtrace, we'll see that indeed the return address it's with our 41, 41, 41. So basically we can modify the execution flow, inject our malware, make it persistent because there's no secure boot, and all. We'll see later another video of the weaponized version of the exploit. Okay, so at this point, back then, I was wondering, like, okay, so it's pretty clear here that this device has support for extended PDUs by hardware and software, but the developers didn't take that into account. Like they were just only creating their application in the firmware to receive regular APDUs, which are up to 255 bytes. But they didn't take into account that they can receive bigger packets, right? So at this point, I was wondering, like, okay, so maybe this issue is happening in other vendors, in other devices. And indeed, it was happening. So basically, using the very same proof of concept that I had with that Android application, I was testing readers and readers and readers, and all of them crashing from different vendors. Okay. We will see some of those vendors. Some of them were stack buffer overflows, like we saw here. Some of them were heap buffer overflows. Basically, because since we are now dealing with a lot of different devices and versions, some of them were bare metal firmware, but some of them they were real-time operating systems or Android or even Linux. So one example, I don't know how to say in English because it's French, Ingenico, I don't know. But this is a very important vendor in the world for payment devices and payment software. And several devices from this vendor were affected for the very same issue. And for instance, I can show you a video here where the thing is to be able to buy these devices with all the production software, so you can perform a transaction. Sometimes it's hard, sometimes it's not, but depending on the vendor or the device, sometimes it's hard. So what I did sometimes also is that a friend of mine in Spain, he has a shop, so he allowed me to test my proof of concept because the proof of concept is only crashing, it's not weaponized. So he allowed me to test with some of his devices in his shop. And as you can see here, this Ingenico device is charging me for 39 euros in this case. So this is an actual production device. And as soon as I try my proof of concept, you will see that reboot in progress message, and it's gonna reboot the device, mainly because in this particular one, it's a Linux system, and what is crashing is a library, and the operating system is detecting the crash and then rebooting the operating system. And since it's not weaponized, the proof of concept, that's why it's rebooting, because I'm not trying to get code execution yet. All right, so let's see. More, very fun as well, several devices with the same issue. Current payment innovations, another one. BB Post, this is a really big one. They have payment devices everywhere, Asia, United States, Latin America. It's a big one, and also several devices affected. WeCC, this is a Chinese vendor, but they have these devices not only in China, but also in Europe and other countries as well, and several of their devices are affected as well. And NextGo, the same, Chinese vendor, but their devices are in Europe and in the US and other places in the world. And yeah, several devices affected by but the same issue. So now, okay, we can get code execution in the firmware of these guys. But what the attacker can do with this? So this could be up to the imagination of the attacker, but from my perspective, I came up with these 3 different scenarios. So let me go to this one that explains everything. So remember that now that we can, over NFC, we can compromise the firmware of the microcontroller that is in this device. We can put a malware there, okay? Our own ARM instructions, basically. So what we can do is, for instance, as I mentioned before, the way it works is that in this particular one, for instance, the computer sends over USB like the start transaction command with the price. But what the malware can do in this guy is change that price. Like if the original price was £50, but it could be the lowest amount possible, like 1 cent or whatever. Even if the device, this particular one doesn't have a display, but some other have displays. You can, since you have full control of the firmware, you can display on the screen the actual price, the £50. When actually what is happening in the background is charging you for 10 cents or whatever. So yeah, and since there's, like I said, in some of these devices, or in this particular one, there's no secure boot, you can make this persistent, and every future transaction, you can make it the lowest amount possible. So yeah, that would be one approach. The other thing that the attacker could do is there's something called contactless magnetic stripe data transactions. As far as I know, this is only happening in the US, and I don't know if some other countries, but mostly in the US, where these credit or debit cards have support for this contactless MSD, where basically sending in clear text the full credit card number and the expiration date over the NFC interface to the reader in this case. So basically, we have in the memory of the firmware in clear text the full credit card number and the expiration date. So the malware of the attacker, what could do in this case is to, like the attacker would go to the reader, inject the malware over the stack buffer overflow that we saw over NFC, and the malware then all the future credit cards that will be used in the reader, the malware will store them in memory or in the flash, and then if the device has internet capabilities, then it can send those credit card numbers to the attacker server. Or if the device doesn't have internet connection, then the attacker can go back to the reader after a few hours or days and interact with his malware over NFC, like sending a command to my malware, and my malware will exfiltrate those credit card numbers that the malware has stored, and then send me those to my smartphone over NFC. So that would be another approach as well. So I have here another video of a weaponized exploit, where it is here. So basically here, as you will see at the first part of the video, you won't be able to see some parts of the user interface, because there are some details and the bank details that we can show for some legal issues. But you will see here first, I'm using a credit card to show that it's working, giving me the receipt. And now my weaponized exploit, basically to prove that the code execution is possible, is what that's going to do, as you will see in a sec, is to show on the screen like an IOActive logo and some silly message, to prove that we can, do whatever we want to with the device. In this case, show anything on the screen, as you will see. Takes some time. And there you go. So, like I said, this is a proof of concept. It's weaponized, but it's just showing this message on the screen with the logo, and this is acting like a ransomware. But like I said before, we can do plenty of stuff with these code execution issues in these devices. By the way, this particular one is Android device. Okay, and now the most interesting one, which is, if you guys remember, I said several times that these readers are connected over USB cable to the host machine, or the host the ATM computer in the case of the ATM. So it would be interesting if once we compromise the NFC reader, our malware running here can compromise the host computer if there's any bug in the host computer software. So for that, what I did was basically I download the IDTech Universal SDK. This SDK is what IDTech provides to their customers so they can interact with these devices over USB. So you can expect to have that in some ATMs, but also in other point of sales or whatever, because this is the actual software that they need to use to interact with the device. So yeah, I just downloaded the SDK and then started to reverse engineer the SDK, because I need to find another memory corruption that allows me to compromise the host. So this would be like, for instance, the host sends a particular command over USB to the reader, and then the reader, which is already compromised with my malware over NFC, as we saw before, is going to send a response over USB, a particular response that is going to trigger a stack buffer overflow, for instance, in the SDK that is running the host. So we can achieve code execution in the host. So for that, the SDK provides several APIs, but I focused in the device init API, because it's this API is used always, because you need, in order to start a transaction, you need to initialize the device. So to me, that was the most interesting one, because I knew that this one is going to be used always by every client that uses these readers. So yeah, so in the SDK is basically a DLL in Windows. So yeah, I started to reverse engineer that particular API, and I found where the code of that API starts to send the command to the reader, and then starts to process what the reader is sending to the SDK over USB. And as you can see here, I saw that in this particular memcopy, the size of the memcopy are 2 bytes that are user control. I mean, those 2 bytes are from the actual USB payload coming from the reader, and there were no sanity checks for those 2 bytes. And the source of the memcopy as well was the USB payload itself. So if the destination buffer in this case wasn't big enough, then we could overflow the buffer and potentially the rest of the stack variables. So yeah, in this case, the stack buffer was 56 hex size, which is pretty small. So yeah, with that main copy, we can overflow the buffer and all the stack variables, and then overwrite again the saved return address in the stack, and then achieve code execution in the DLL, which is in the SDK. So again, I know this could be a bit confusing, but we are chaining 2 attacks here. We are first compromising the firmware of the NFC reader over the NFC interface, as we saw before. Then we inject a malware in the microcontroller of the reader, and then that malware of the reader is gonna compromise the host over USB with that other stack overflow that we just saw in the DLL. So we're chaining 2 attacks here. And yeah, and remember that the host in this case could be the ATM computer, or the ATM in the point of sale, or other device. So to create a quick proof of concept of this, to see that I can actually compromise the host, instead of creating my own malware in this device, to make it quickly, because creating a malware could take some reasonable time, I used a Raspberry Pi with Gadget FS. So the Raspberry Pi has USB, and the Gadget FS allows you to emulate any USB device. So basically, with the Raspberry Pi, I was emulating the NFC reader. And so yeah, you can, with Gadget FS, you can provide all the USB information for the endpoints and the product ID, device ID, vendor ID, sorry, to emulate this particular one. So the SDK will believe that my Raspberry Pi will be this NFC reader. And then with Python as well, you can send whatever you want over USB and receive from the SDK as well over USB. And this is actually the proof of concept that makes to trigger the stack buffer overflow in the SDK in the DLL. And as you can see here, with WinDebug, you can see the crash of the stack buffer overflow with this proof of concept. So with this you can prove that code execution is also possible in the host from the previously compromised NFC reader. And yeah, and this DLL, this SDK is pretty vulnerable. Besides that stack buffer overflow, there are more than 20 similar to these ones, but we don't need to cover all of them, right? We just need one. Okay, so for the ATM scenario, so like I said before, I have many years of experience working with ATMs, reverse engineering ATM drivers, reverse engineering ATM devices firmware, working with the USB communications, and also I have experience working with XFS, which is the middleware that basically every ATM has to interact with the hardware to perform, for instance, a cash out or interact with the card reader or whatever. We will see more details about that. And like I said before, these IDTech devices, the Kiosk 3 in particular, is used at least in NCR, WinCore, Diebold, Fujitsu, and Hyosun ATMs, probably more, but these at least are confirmed. So what we can do with the ATM? So with the ATM, from my experience, I believe we can do two things, maybe more, but this is the things that I came up with. The first one would be similar to the other one that we saw before, that we can steal from the memory of the device those credit card numbers. I mean, we can compromise first over NFC the reader, and our malware will collect those credit card numbers that will be used in the future with the ATM. And in this case, as these devices, the IDTech Kiosk 3, doesn't have internet connection, or capabilities to get internet connection, then the attacker in this case will have to go back after a few days or hours to the ATM and interact with the malware and then exfiltrate those credit card numbers and expiration dates from the ATM. But the most interesting one would be the ATM jackpot, like chaining these two issues, like compromising the firmware of the reader and then compromising the ATM computer, then performing a cash out, okay? So that would be the second scenario, and we're gonna explore this. So, like I said before, the malware that is running in the NFC reader that has been compromised is gonna, with those USB communications, is gonna, for instance, if the ATM computer is using the IDTech SDK, as we saw before, which is pretty vulnerable, we're gonna trigger one of those stack buffer overflows with those USB communications. And now we have code execution in the ATM computer. Now, how you can, from the ATM computer, you can perform the cash out. So what the exploit would have to do here. So if some of you guys have experience working with ATMs, once you have code execution in the ATM with admin rights in this case, it's just a matter of time to be able to perform the cash out. Sometimes it's very easy, sometimes it's hard because they put some layers of security. But the problem is that the way the ATMs are designed, it's impossible to make it 100% secure. It's impossible. There's no way. So in this case, like the way I normally do is I interact from the ATM computer with XFS, which is the middleware that allows you to interact with the cash dispensers in this case, as we will see in a second, and then your XFS malware that will be placed over USB in the ATM computer. It will perform the cash out. But something interesting here as well is that you are not, from the attacker's perspective, you are not limited to the IDTech SDK if it's running there, because since you have full control of the firmware of the reader with your malware, you can act as another USB device. and let's say there is a USB camera driver that is vulnerable in the ATM, then you can act as a USB camera and exploit that issue in the driver of the USB camera, for instance, or camera or whatever device, other device. So that's something also I think it's interesting to take into account. So yeah, so XFS. I mean, there are more ways to perform a jackpot from an ATM, but the most obvious one is using XFS. XFS is a middleware, it's a standard that provides some APIs, so you can use those APIs to interact with the hardware, in this case the cash dispenser. Some ATM vendors, for instance, they try to authenticate the binary that is interacting with these APIs, but in the end, since you have full control of the code execution in the operating system, in this case in the ATM, in the end, that authentication is happening in the same operating system. So in the end, if you have full control, you can also bypass that. Also, in some other ATMs, there are no even authentication or whatever, so you can just call the APIs and interact with the ATM hardware. So in this case, for instance, this is one example of one of my XFS proof of concepts, where you can see you are using the WFS Open API to open a session with the device, in this case, the cash dispenser. And then we are setting some details like, hey, I want a number of bills from this number of cassette and so on. And then you call other APIs like the execute to actually execute the command to perform the cash out. So at this point, you could be thinking, okay, but have you ever tried this chain of attack in an actual ATM? And I can tell you that yes, but the problem, the only way to prove this was in a lab of production ATMs, because you can buy ATMs, but with the production software and everything, it's to me it's really hard to get that. I don't know if maybe you can get that, but I couldn't. So the problem is that there are some NDAs involved, so I can't tell you what ATM I was working with and what driver it was involved in this issue. But yeah, I had many questions about this in the past. So if some of you have are affected with this in your ATMs or whatever, my recommendation here is that well, first, I think here you have enough technical details so you can, if you have the motivation and the time to try by yourself. But also, if you are concerned about this, my very first recommendation would be to make sure that the firmware of the NFC reader is already patched, because, for instance, IDTech provided already a new firmware version to patch this issue. Because if you fix this issue here in the NFC reader, then the attacker won't be able to reach the issues that are in the SDK or the driver in the ATM computer. I mean, the attacker could if the attacker has physical access to the USB cable, but at least over NFC, the attacker won't be able to compromise this guy, and then won't be able to compromise the ATM computer. So regarding disclosure, all of these vendors were contacted. All of them, they told us they fixed the issues. And some of them, they provided the patch, so we could analyze the patch and make sure that it was properly fixed. But not all of them provided the patch. And yeah, and we waited almost 2 years. Because as you saw, many vendors and parties were affected by these issues, and the problem is really hard to patch some of these devices, because some of them, they don't have remote update capabilities, so they have to go physically to some of these devices to upgrade them. So as you can imagine, it's really hard. And nowadays, even there are newer firmware versions to fix the issue. Now there are still vulnerable devices out there, because there are hundreds of thousands of devices out there with these issues. But yeah, at least I think we gave them a lot of time to patch and learn about this. So yeah, I think that's everything. Thank you guys, and if you have questions, go ahead. Happy to answer anything. Thank you.